Up to this point in the course, we've talked a lot about calculating probabilities exactly, as well as just a little bit about how we could simulate probabilities using Monte Carlo simulation. But there are other ways to grapple with probabilities, and the one that I want to talk about right now is how we can bound probabilities using specific inequalities, or very common inequalities. And the reason why we may want to do this is if we want to be able to prove whether or not a probability falls within a certain range. And we know that simulation doesn't really allow us to prove things like that. It can just allow us to see patterns, and even then it can be hard to establish those patterns. And so one example where this may come up is that if you were an expert witness in a court case and you don't want to defend an approximation that you've obtained through Monte Carlo simulation or other methods. So if you're that expert witness, you would probably rather state that a probability is less than or equal to a specific probability than trying to approximate it, which would open yourself up to criticism. And so that's our goal here, is we need to establish these inequalities that allow us to bound probabilities in this way. And so we'll march through a couple inequalities in this segment, and we'll just start with the Cauchy-Schwarz inequality. Which is a specific version of Holder's inequality, if you've heard of that. Okay, so let's start by just stating the inequality here. So this is used to work with two random variables. So let's say that for any two random variables, x and y, the expected value of x multiplied by y squared is less than or equal to the expected value of x squared multiplied by the expected value of y squared. So that's our general form. That's the most general form of the Cauchy-Schwarz inequality that we can work with. But that's not necessarily the most commonly used form. So more commonly, at least in probability and statistics, we state this as, well, the absolute value of the expected value of x multiplied by y is less than or equal to the expected value of the absolute value of x multiplied by y, which is less than or equal to the square root of the expected value of the absolute value of x squared multiplied by the expected value of the absolute value of y squared. And then you'll note that this is going to be equal to the square root of the expected value of x squared multiplied by the expected value of y squared. So this is the general form if we think about the end result that we use in statistics. And so why might that be an expected or a more commonly used form? And that has to do with our covariance and our correlation that we'll see in just a minute. So I will just make a couple remarks here just to remind you of a few things with the Cauchy-Schwarz inequality. The first is that this is a special case of Holder's inequality. And so that might be interesting kind of from a historic perspective, or if you're interested in making connections between Math 440 and other classes. And the other remark I want to make is that strict inequality holds here. Oh, strict equality, I'm sorry. Strict equality holds if x and y are uncorrelated. And so you can think about how that applies. Now, I think linking this to the statistical interpretation, or in terms of the application where we're thinking about correlation here, is very important. And so let's do that now. let's recall the definition of correlation. So the correlation between random variables x and y is equal to the covariance of x and y divided by the square root of the variance of x multiplied by the variance of y. We know that correlation is between -1 and 1. And so let's look a little bit deeper and see how this relates to this inequality that we've worked on here. And so let's just also think about the definition of covariance, and let's see how that hooks up with this. So what we're going to do is, if we let x and y have means or expected values, mu x, mu y, respectively, then we have our notation set up, and we recall that the covariance of x, y is equal to the expected value of x minus its mean multiplied by y minus its mean. And so now we start to see where the Cauchy-Schwarz inequality comes in. So if we write that expectation with an absolute value out front, then we're in the framework of the Cauchy-Schwarz inequality. And what that inequality says is that this is going to be less than or equal to the square root of the expected value of x minus its mean squared times the expected value of y minus its mean squared. And now if we were to rearrange this inequality, we actually can establish the bounds that we have on correlation. All right, so notice that, I'll just write that we're rearranging. We find that the absolute value of the correlation of x and y is equal to the absolute value of the covariance of x, y, divided by the square root of the product of the variances. Notice that I don't need to apply the absolute value down here in the denominator because we know that variances are non-negative. And we know that this is going to be less than or equal to 1 just through a simple division on both sides of this inequality that we've established up here. And so this is one of the key areas where, or applications where we see Cauchy-Schwarz in an everyday type of result. And so this leads to the interpretation, right, that our correlation is between -1 and 1. The second inequality that we want to establish is called Jensen's inequality. And Jensen's inequality allows us to understand what's going on with the expected value of a function of a random variable. So in terms of a statement of this inequality, we'll start with some random variable x. So for any random variable x. And it's a two-part inequality, so it depends on what's going on with g. And we should specify that this function of g maps from the reals to the reals. And now we have two parts. Well, if g is a convex function, then the expected value of that function of the random variable, of that convex function, is greater than or equal to the function applied to the expected value of x. If g is a concave function, then we'll see the reverse, that the expected value of g of x is less than or equal to the function of the expected value of x. And so this is a very useful inequality in terms of bounding a number of types of functions that you can think of, and you may have wanted to apply this function but didn't yet know what it was. But before you move on to some examples, what I'd like to do is just recall a little bit about convexity. So recall that a function g of x is convex if its second derivative is greater than or equal to 0. And this is really the easiest way to check whether or not a function is convex, but it does require that this function g is twice differentiable, which may not always be the case. So that's the requirement that you've probably learned in terms of your calculus classes, but we can also think about a geometric interpretation of convexity. And let's think about this. So let's just draw some example of a convex function. And so, for example, we could think about the function x squared. And so that's our convex function. And we know what a graph of x squared looks like, certainly. So we have this parabolic graph here. Pardon my poor drawing skills on this pad here. And the geometric interpretation of this convex function is that convex functions lie below lines connecting any 2 points. So if we took a point here on the function as well as a point here and then connected those with a line, then what you're going to see is that the function falls below that line. Now, if it was a concave function, what you'd see is that the function would lie above that line connecting 2 points. So that's one way to deal with this. Another way to think about convex function is that a convex function lies above all of its tangent lines. So if then you think about a point here and establishing that tangent line there, what you're going to see is that that function lies above its tangent line. And so that is going to happen with convex functions. Similarly, over here at this point, if we draw the tangent line, what you'll see is that the function still lies above that. And so that's another way to check for convexity of these functions, which may be easier, especially if you have a non-twice differentiable function, such as the absolute value. And so now you might be wondering, okay, well, what are some examples that we might want to think about here? And we've already seen a couple. And we've already established a nice way to check Jensen's inequality if you forget what it is. And so the first example here is the relationship between the expected value of x squared and the expected value of x quantity squared. And so let's say you've forgotten Jensen's inequality. Well, you know that the expected value of x squared has to be greater than or equal to the expected value of x quantity squared, due to the definition of variance and the fact that variance is non-negative, right? So we already knew this. From properties of variance. But this is a really nice first example because it allows you to always go back and check your work, right? So if you know that x squared is a concave function, so you can check the direction of this inequality based on this one example. And then if you accidentally have this sign reversed, well, you can just think about variance and then correct that quickly. Now let's think about another function that will commonly hit, especially in statistics. And so we can let x be a positive random variable. And then now let's think about, well, what's the expected value of the natural log of x? And how does that relate to the natural log of the expected value of x? So if we think about what the plot of the natural log looks like, right, we're going to have 0 here. On the y-axis, we're going to have 1 here. Well, we know that for values between 0 and 1, the natural log is negative, and then it'll become positive at 1. Sorry, that's not quite right. But if you look at the shape of this, well, certainly this is a concave function. You can verify that by looking at tangent lines. and noticing that the tangent lines fall above and not below. You could also connect 2 points on the natural log here and then connect them with a line, and you'll see that the function lies above it. And so what we know is that the expected value of the natural log of x is less than or equal to the natural log of the expected value of x. Now we could go through and prove this, but your book has a quite elegant and understandable version of the proof. So we're going to omit that at this time, and I encourage you to read the book in order to look at the proof. The fourth and final inequality that I want to discuss in this segment is Chebyshev's inequality. And Chebyshev's inequality actually allows us to refine the bounds that you could think about defining using Markov's inequality. I omitted those bounds because they're so crude, and we really want to use Chebyshev's instead. But Markov's inequality gives us this really elegant way to prove Chebyshev's inequality, which is why I introduced Markov's inequality. And so let's look at what this inequality says. So this inequality says let x be a random variable with expectation mu and variance sigma squared. And we're also going to focus on a positive constant a. Then what the inequality says is that the probability of the absolute distance between x and mu being greater than or equal to some constant is less than or equal to the variance of x divided by the constant squared. Now that's not necessarily obvious right away, but let's look at a proof here. So we've already looked at the proof of Markov's inequality, which used the fundamental bridge. So let's set this up, and let's just start by writing down what we want to start with on the left here. So we're interested in the probability that the absolute distance between x and its mean is greater than or equal to some constant a. And while absolute values can get a little bit messy to work with, so let's first rearrange or rewrite this in terms of the squared quantity x minus mu rather than the absolute value. And we know that that's going to preserve the sign of our inequality inside this probability statement. Okay, so now all we would need to do is think about, okay, well now we have a random variable in here on the left of that inequality. We have a constant on the right, so we can apply Markov's inequality, which says that that probability is less than or equal to the expected value of x minus mu quantity squared divided by the constant a squared, which is on the right side of the inequality. And so remember that that's by Markov. And then all we need to do is remember what the definition of variance is. Well, the variance is the expected value of the square difference of x and its mean. So this becomes the variance of x divided by a squared. And so we've established Chebyshev's inequality. But we want to actually be able to apply this. And so we actually have a more common form for application. And so I'll just call this the form for application in terms of establishing bounds. And what happens here is that a lot of folks rewrite Chebyshev's inequality in this form. So they look at the probability of the absolute distance between x and its mean being greater than or equal to c times the standard deviation of x. Now notice what's going on here. Well, this is just a constant. This c times the standard deviation of x is just some new constant. So we're not really changing anything. We're just saying that a is now equal to c times the standard deviation of x. And so we know then that this would be less than or equal to, well, it would be less than or equal to the variance divided by this constant squared, and that would square the standard deviation of x, which would give you the variance. So this happens to be 1 over c squared for some positive constant c. And while this might not help you prove other results, this really does help you establish bounds for any generic probability distribution. So let's take a look at how that works. So in this example, we're going to be looking at how we can get bounds for probabilities as we're a certain number of standard deviations away from the mean, and that should remind you of the 68, 95, 99.7 rule, or the empirical rule from the normal distribution. So really what we're talking about here is a generic empirical rule that'll work for any distribution. And so the first way we can write this is in terms of this reordered or rearranged Chebyshev's inequality. So if you think about, okay, well, what's the probability that x minus mu is greater than or equal to 1 times the standard deviation of x? Well, that's going to be less than or equal to 1, which isn't a very interesting result, because all this says is that, well, the probability that x is at most 1 standard deviation away from its mean is at most 1. Well, all probabilities are at most 1, so that's not very interesting, but it'll give us crude bounds. They're not as specific because we're not assuming anything about the distributional shape for this random variable. So that's why they're going to be rather crude bounds. So if we then look at what happens with 2 standard deviations, well, Chebyshev's inequality says the probability that x is at most 2 standard deviations away from its mean is less than or equal to 1 divided by 2 squared, so that's equal to 1/4. So it's less than or equal to 1/4, and for 3 standard deviations, we're going to be less than or equal to 1 divided by 3 squared, so less than or equal to 1/9. And so this gives you a general empirical rule for any distribution. You can check that this is true for the exponential distribution, the beta distribution, the gamma distribution, the chi-square distribution, the uniform distribution, the binomial distribution, the geometric distribution. This is going to give you bounds for these. And notice that we aren't restricted to whole numbers on these bounds either. This will work, but the result is very crude. But that is one thing that Chebyshev's inequality can give us. So if you think back to that court case, even if the bounds are crude, if you can prove your point using this, you can't argue with it because it is an established result that we have proved.